Swayam Prabha. Digital India. Educated India.
Good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. We are actually almost done. We have only 2 lectures left. What we've been doing over the past several lectures is we have been in module 4 of the course. So, module 1 was largely an introduction. Module 2 and module 3 we went through analysis of rigid pavements. In module 2 we looked at analysis of rigid pavements using classical methods or analytical methods, where under a series of simplifying assumptions, some of which can be very serious assumptions, under a series of simplifying assumptions, some very smart people solved a differential equation, the Sophie-Germain equation. They solved a differential equation and they developed certain solutions. Solutions for what? Well, if you apply a load to a slab, what are the stresses, what are the strains, what are the deflections? That's basically what we mean by solutions. Those were analytical solutions in the sense that they were closed form. That is, they were formulas that we could put into a calculator, we could solve by hand, maybe on a spreadsheet we could do it. There was no significant mathematical background required to use the equations, although developing the equations was a completely different matter. But fortunately, many smart people, starting from Professor Westergaard, took care of that for us. We also looked at Freiberg theory for the analysis of dowels. Now, the issue we had talked about at the end of module 2 is that these analytical methods, they make certain simplifying assumptions which are very serious assumptions. The biggest of which is probably the infinite slab assumption, that is, the slab is very big in size compared to the radius of the load. That assumption leads to significant overestimation, maybe by about 50% or more, in stresses as compared to realistic slabs. So, that is why from the 1990s onwards, progressively the world over we have been abandoning the use of these analytical methods. They are still used in some places here and there, but largely we have been abandoning the use of analytical methods in favor of these new sort of methods which are the numerical methods. That is what we learned in module 3. And by numerical methods, primarily I am talking about the finite element method. So, of course, this is not a class on finite element method. It's not possible to teach a finite element method during just a couple of lectures. It's in a class on rigid pavement design and analysis. But I encourage all of you, particularly those with a civil and mechanical engineering background, to take a formal course on finite element method. It's a very, very useful topic to learn. Anyway, the key aspect of the finite element method is that we basically, instead of solving a differential equation with certain assumptions, which can be quite hard, we don't make those certain assumptions. Instead, we make certain approximations about the solution, and then based on those approximations about the solution, we actually convert the differential equation into a large number of simultaneous linear equations. That I am not talking about 3 or 4 equations, thousands, tens thousands, lakhs, millions of equations. We can have a very large number of equations that have to be solved together. Obviously, it is not going to be done by hand. In high school, maybe you solved a 3 by 3 system and that itself made you sweat quite a bit. You are not going to solve millions of equations by hand. Fortunately, computers are very good at solving these equations. So, the real development that we have seen in rigid pavement design analysis over time has been the use of digital computers, and that has mainly come down to the fact that those computers are very, very good at solving a large number of system of equations simultaneously, which is exactly what the finite element method requires in order to use it. So, we saw lectures on FEM, we saw how using the so-called MCZ plate, we can model the behavior or the not performance, we can model the response of a single slab. And then we saw that if we have multiple slabs connected by dowels or tie bars, we have other models. So, we can have other sort of models based on beam theory to model the dowel bars or the tie bars. And the wonderful thing about the finite element method is we can completely fold that physics. We can incorporate the effect of those steel reinforcing bars into the model for the JPCP slabs themselves. It's quite remarkable what we can do using this stiffness matrix. We can fold them together and now we can solve a system of equations which involves not just individual slabs, which is all we could really do with Westergaard's theory, but we could also calculate simultaneously the effect of load transfer due to dowel bars and tie bars, which is quite a remarkable thing that the finite element method allows us to do. Now, of course, the downside of FEM is that compared to the analytical methods, it was quite mathematically intensive. There was a lot more effort that was needed to be done. However, in practice, it's never done by hand. There are a large number of FEM programs out there, and we looked at one particular one called iSlab, but there are many others also. There are a large number of FEM programs that can actually very easily do these calculations for us. So, in practice, we don't actually use the finite element method in actual design. We use, or we don't program the finite element method. We don't actually use the finite element method also, which I'll get to in a second, but we don't program the finite element method. Instead, we use these ready-made solvers to do the calculations for us. And moreover, in practice, for design purposes, we don't even use those ready-made solvers. Instead, we use what are called surrogate models. We use some sort of approximations which are built by performing a large number of finite element simulations, so that we can very quickly calculate the stresses. The problem with, one of the problems with the finite element method is that besides being mathematically intensive, it can be slow. It can take quite a lot of time to perform these calculations. So, to overcome that, a lot of surrogate models have been developed. Now, in module 4, which was on the mechanistic empirical design of rigid pavements, we have been looking at two implementations of mechanistic empirical design. So, firstly, we saw what is mechanistic empirical design, what is the philosophy of mechanistic empirical design, and very importantly, we learned about the use of fatigue theory and fatigue damage in pavement analysis, which is really a big move away from what was being done previously in the empirical design methods. So, what we learned two big implementations. There are many implementations of ME design in the world. We learned two major ones. The first and probably the most sophisticated implementation was the AASHTO MEPDG, the Mechanistic Empirical Pavement Design Guide, which is used largely in North America and has been used very successfully in other parts of the world also, although more on research type of questions. So, in MEPDG, we saw that the calculation of stresses was built using certain neural networks. So, of course, iSlab was the computational code, it was the finite element engine, but then 4 neural networks were actually built on top of it using what's called an equivalent plate concept. This is quite remarkable when you think about the fact that these were developed in the 1990s. Today, it's relatively simple to develop neural networks. Actually, many of our BTech students here are also able to develop neural networks, it's not particularly difficult. But to do that in the 1990s was quite an achievement by itself. So, the surrogate model which was used in the AASHTO MEPDG was actually a series of 4 neural networks, and various combinations of them are used to perform the analysis. Okay. After looking at the AASHTO MEPDG, we looked at a great deal of detail. We saw how the calculations are done, we saw how optimization can be done, how reliability is incorporated, etc. We then moved on to looking at IRC 58. So, IRC 58 is the Indian code of practice for the analysis and design of rigid pavements. In particular, we have been looking at the 4th revision or the 5th overall edition of IRC 58, which is IRC 58 2015. Now, I should point out, as I have been saying for previous lectures, I am going to just say IRC 58 in this class. I mean the 2015 revision, that is the 4th revision of IRC 58. So, we are not looking back in history. IRC 58 actually has quite a fascinating history. We briefly talked about that in one of the lectures. It started in 1974, it used Westergaard's theory, progressively started improving its model, and for around 20 years now, we have been using fatigue damage, the concept of fatigue theory inside. Now, IRC 58 is not fully a mechanistic empirical design, in the sense the failure criteria is still based on the concept of fatigue damage alone. So, basically Miner's hypothesis, which says that failure occurs when fatigue damage is equals 1, that is still used in IRC 58. I had talked about the fact that this is okay, scientifically there is nothing wrong with it, but the problem is fatigue damage is not really related to performance directly. Performance is usually based on distresses, cracking, faulting, punch outs, crack width, etc. So, we are, as pavement engineers, we are actually interested in, let's say, cracking or faulting. So, fatigue damage does not directly give us cracking or faulting. So, the fact that the IRC 58 approach actually stops at fatigue damage leaves it as sort of an incomplete code. There is still much more that can be done. Fortunately, the code is continuously being revised. Now, if the last revision was in 2015, I think it is due for another revision at some point, and maybe the next revision should be based on moving from just a mechanistic based failure criteria to more of an mechanistic empirical approach, where the failure criteria is more empirical or based on distresses rather than based on fatigue damage. Anyway, in the previous 2 lectures, we actually went through a great amount of detail in IRC 58. So, like AASHTO MEPDG, IRC 58 also uses finite element analysis in order to calculate stresses. And like AASHTO MEPDG, IRC 58 does not directly use a finite element solver either, because that is too computationally intensive. Instead, what the developers of the code did is they used a program called IIT SLAB 2, which is developed at IIT Kharagpur. They used that program and they ran hundreds of simulations. Instead of developing a neural network, they instead developed some relatively simple but dimensionalized regression equations. If you get a copy of IRC 58, then there is no companion software containing IIT SLAB. Unlike, let's say, IRC 37, which is used for flexible pavement analysis and design, which contains a companion software which is called IIT PAVE. IIT SLAB is not directly provided with the CD itself. Instead, what the CD has is an Excel sheet where the developers have thoroughly tested and ensured the correctness of these regression equations that were developed to calculate stresses. And I had pointed out in that lecture that one of the shortcomings of those regression equations are that they are dimensional. So the authors have not non-dimensionalized the equations. Because they are dimensional, then it is very, very important to use the correct units. Units are provided for all the inputs, but you have to carefully read what the units are and provide only those inputs in only those units. It's not a question of having a consistent system of units, because consistent system of units, what we use in Westergaard's theory, for example, that is important only when you have non-dimensionalized equations. When you have dimensionalized equations, the critical part is not to have a consistent system of units. The critical part is to follow whatever system of units is being recommended by the particular formula. So we did an example of that where we saw how to use a particular system of units as recommended by IRC 58 to calculate the stresses. We also talked about how to incorporate climate considerations, and in the previous lecture we did a full-fledged example of an analysis and design of a particular rigid pavement, where we saw that really a lot of the details that go into doing the design of rigid pavements is actually on the traffic side. It's not good enough to just say that we need an axle load spectrum. Even after you estimate an axle load spectrum, estimating the actual number of vehicles or the actual number of repetitions of axles for design purposes is quite a challenge. We have to know what is the vehicles in each direction. That's straightforward, that's not particularly difficult. We have to know the cumulative number of vehicles over the entire service life. That's also not very difficult. We have to then know what is the fraction of the vehicles during the day, what is the fraction of vehicles during the night. Of those vehicles during the day and night, which fraction of them are critical in terms of their lateral position or where they are placed on the edge. Among those also, for nighttime calculations, it's important for us to know what is the fraction of the vehicles whose wheelbase, that is the distance from the front axle, the front steering axle, to the first axle and the rear axle. Which of them, what fraction of them have a wheelbase which is within a single slab such that it can cause top-down cracking. And once we know all this, we then have to know what are the average number of axles per vehicle, what is the frequency distribution of each axle, that is the front axle, then rear single, tandem or tridem. For these 4 classifications, we have to know what is the distribution of the axles, and then we have to know the full axle load spectrum for each of them itself. So as you can see clearly, perhaps the most complicated thing, it does not seem particularly scientifically impressive, but it's actually the most important. The most complicated part of doing the design using JPCP for IRC 58 is to actually fully be able to characterize traffic. Lot of subjectivity involved in that, and it's also an area of ongoing research. All right. So in the previous lecture, we then saw that we can calculate, once we calculate the number of repetitions for each axle load, axle type and the corresponding load. So for example, for single axle, we would have a variety of load classifications, and then for each of those loads, we then calculate what is the stress. From the stress, then we go on to calculate the stress ratio, which is simply stress divided by the flexural strength. From the stress ratio, we use our SN curves, which comes from fatigue theory. We use the SN curves and we calculate the allowable number of repetitions. The total number of repetitions by the allowable number of repetitions for that axle is then called the fatigue damage, and we sum it up over all the axles. We finally get the cumulative fatigue damage. In the IRC approach, the CFD, the cumulative fatigue damage, must be less than 1. In other words, Minor's hypothesis is being used. As I had mentioned in the beginning, that's not necessarily the best way to do it from an engineering perspective, but nonetheless, that is the way it's being done. Now, in all this discussion, several times over previous lectures, I have been talking about that SN curve. Again, what is an SN curve? If I draw it on the screen over here. So an SN curve in a logarithmic scale, it's basically giving you the stress or the stress ratio versus n, which is the, or nf, which is the allowable number of repetitions. And generally, this is a logarithmic curve, so it tends, a semi-logarithmic curve, so it tends to be like this, where this nf is on a log scale. Okay, so this is what an SN curve is, and I have been pointing out a very important number, 0.45. This number I have called an endurance limit. And what it basically says is, below a certain value, certain threshold of SN, the number of allowable repetitions basically goes to infinity. That is, the SN curve becomes flat in this way at some value which is 0.45 SR in the SN curve which is used in India. That number is called the endurance limit. The reason I am emphasizing is, in today's lecture, which we're going to talk about the consideration of fibers, we are going to be revisiting this endurance limit, and we're going to talking a little bit about whether we can change it and under what conditions we can change it. The one thing I should point out, I had mentioned this in the lecture on fatigue, and you can go back and revise that lecture. The very existence of the endurance limit is not a universally accepted fact. In the approach used in the Indian code, we do consider that the SN curve has an endurance limit. But if you look at the Ashter MEPDG, what SN curve they are using over there, it does not assume the existence of an endurance limit. So sometimes you have an endurance limit, sometimes you choose a model which assumes the existence of an endurance limit, sometimes you choose a model which does not assume the existence of an endurance limit. I personally feel endurance limit is something to say that you can have an infinite number of repetitions is a very, very serious assumption to make. You're saying something very, very big about the performance of the material or performance of the structure. So I think in my personal opinion, it's better not to use endurance limit because it's a very serious assumption to make. We cannot guarantee durability of the pavement long enough to satisfy this assumption that we can have an infinite number of repetitions. Anyway, my opinion aside, so I just wanted to point out and recall that there is such a thing as an endurance limit as per IRC 58. Now, in today's lecture, we are actually going to have some consideration of fibers. It's going to seem somewhat unrelated that we've never mentioned fibers so far in this class, but actually, as we'll see, in fibers in concrete is becoming increasingly common all over the world as well as in India, and there are various benefits of using fibers also, which we'll talk about in today's lectures. So I'll talk today about the role of fibers in FRC. FRC, by the way, is fiber reinforced concrete. FRC is a material, it's not a type of pavement. So JPCP, JRCP, CRCP, PCP, these are types of pavements. They're all made of plain concrete, or they can be made of fiber reinforced concrete. So it can be made of piece. So the opposite of FRC, that is without any fibers, would be just PCC, Portland cement concrete, or just CC, cement concrete. So FRC is particularly if we add fibers. We'll talk about what type of fibers and what dosage in a bit, but FRC is what we call this particular material. So we don't have an FRC pavement. We can have an FRC JPCP or a JPCP that's using FRC. But FRC on its own is not actually a pavement type. And then finally what we'll see is we will see how do we design JPCP with FRC. I'm not going to do the entire repetition. As we'll see, the design of JPCP with FRC is very similar to the design of JPCP with normal PCC, but there's a slight correction which we have to make actually to the endurance limit, and we'll talk about that in today's lecture. So we're not going to repeat an entire exercise on it. I'm just going to tell you a little bit on how we can modify the JPCP design we learned previously to account for the existence of fibers in our concrete. Okay, so let's understand what are fibers. Intuitively, all of you probably know fibers. I mean, you're all wearing clothes, so your clothes are also made of fibers. So all of you see and you have an idea of what is fibers. So fibers are basically thin threads. So it's a particular type of shape. More than anything else, a fiber is not a material really, it's a shape. And so a fiber consists of thin threads which could be natural or artificial materials. They are used in rigid pavements to provide reinforcement for cracks. This is very, very important, and we'll see a revisit of this concept in the next lecture, which will be on CRCP also. The purpose of adding, whether it's steel reinforcement or whether it's fiber reinforcement, either way, the purpose of reinforcement in pavements is not to add to the strength. Fibers do not improve the strength. Instead, what fibers do is they provide reinforcement for the cracks, that is, they prevent the cracks from opening up too much. They do not prevent the formation of cracks, and strength is basically related to formation of cracks. They do not affect the formation of cracks or the initiation of cracks. They affect the propagation of cracks. So in rigid pavements, fibers is to provide reinforcement for cracks. That is, once a crack develops, once a crack already forms, then these fibers, they bridge the cracks. They basically make sure the cracks stay together and the crack width doesn't open up too much. But they don't prevent cracking as such. That's something very, very important to understand. Whether it's fibers, whether it's steel reinforcement in JPCP and CRCP, steel does not prevent cracking, or fibers do not prevent cracking. Instead, they prevent the crack from opening up too much after the crack has been formed. That's how we call it reinforcement for cracks. Okay, so when I say that fibers can be natural or artificial materials, what are some examples of materials? Well, from artificial ones, the most common ones are steel fibers. Perhaps some of you have seen steel fibers in the past, they're quite heavy. We can also have polymers. This is actually quite common. So one type of polymer could be polypropylene, fairly common. There's also PPA, and there are a couple of other fibers which are also out there. An interesting area of study has been carbon fibers or carbon nanotubes. And then there's also glass fibers. So those are fairly interesting and research level applications of different types of fibers. They all have certain properties and certain behaviors, some of which we'll talk about today. Now, the use of natural fibers is used less often, unfortunately, and tends to be due to performance and durability related issues. But it's also possible to use natural fibers. So, for example, we can have jute fibers and coconut fibers. Now, naturally, these jute and coconut fibers, they have to be dried out, because if it's naturally wet, it's going to affect the mix design, and B, it's going to decompose over time. So these fibers have to be fully dried out. So when we say natural, it's not to say that they don't have to go through some amount of a manufacturing process, that they don't need some amount of processing. They do need some amount of processing. They need to be cut accordingly. They need to be dried. They may need to be chemically treated to enhance their properties. But at least the core material is natural. It's not, say, from plastic or from steel. So the environmental effects of using these ideally should be less, but it's not negligible. So these are some various natural fibers. So these are different materials, but that's looking at it from a materials perspective. We can also look at fibers from a geometric perspective. Before that, I just wanted to show you this picture. This is, by the way, taken from IRC SP46. This is a particular code which is, it's not a code, it's a special publication. So again, an IRC code is a legally enforceable document. It's something that contractors are required to follow. By the way, it's not something that researchers are required to follow. In research, you are welcome and encouraged to break ideas and make new assumptions. IRC codes, contractors are required to follow in their tenders and in their construction process. IRC SPs, or special publications, and BIS has the same concept, but special publications are not legal documents yet. They are sort of experimental documents. They are meant to put an idea or provide some guidelines, but it's not reached the point yet where the knowledge is so well known that it can actually become a legally enforceable code. So a special publication need not be legally enforceable. It's just meant to be as an informational document, hence special publication. So IRC SP46 is actually related to fibers. We'll talk a little bit more about it later, but I just took this photo from there to show you some different examples of fibers. So example, here what we have, the most common one, which I'm sure all of us have seen at some point, is steel fibers. So they're very small. You can just hold it up with two fingers, but they're made of steel. They tend to have a shape. They could be plain, they could be crinkled. They have several possible shapes. Then you can have polymeric fibers. So you can have polymeric monofilaments, that is, you just have individual threads. That could be, example, a polymer wool, for example, which could be used for insulation. You can have polymer fibrillated, that instead of just having these thin thread-like fibers, the polymer fibers can have some sort of structure and some sort of geometry in them, which is what you call fibrillated. Or you can have some polymeric macrofibers. Macrofibers are, we'll talk about what macrofibers are in a second. So these are just some different examples of what these different fibers could look like when you're mixing them into FRC. Why does FRC work? As I said previously, the purpose of fibers is not to prevent cracking. Fibers do not prevent cracking. Instead, what fibers do is they control crack propagation, that after the crack has formed, fibers then affect how the cracks are going to propagate. So the mechanism by which they do this is through bonding with the cement paste. So what I have over here, if I assume this gray box over here represents a little blob of cement, and I've got a fiber inside. The cement paste is actually going to bond with the fiber. That is, it's going to stick basically to the fiber. So now if a crack, for example, is trying to go through, that somehow this blob of cement paste has been cracked and now a crack is trying to propagate through. Once the crack reaches the paste, then it actually turns from a problem of crack propagation, it turns into a problem of fiber pullout. That as this crack is trying to open up, this fiber itself is being stretched. And the stretching is happening, what's preventing the stretching from happening is the fact that the fiber is adhesed or sticking to the cement paste. That is the mechanism by which this crack propagation converts into tension inside this fiber. Now, it could be relieved, for example, by complete breakage of the fiber, that the fiber could split into two because it's being pulled apart. That's generally rare. These fibers are very, very strong in tension. So, it's very difficult for that to happen. It eventually happens because whatever this tension is, it tends to exceed the bond strength of the fiber, and that's so you tend to have what is called a pull apart or a breakaway sort of failure. That is, so let me just draw this formally. So if I have a crack propagating over here and then I have a fiber going through here, what's happening is as these two faces, the cracks are opening up, the fiber which is fully bonded with the cement paste, the fiber is also being pulled apart. It's being pulled apart, but because it is fully bonded with the cement paste, there is resistance to that pull apart which is developing due to that bond. Eventually, however, as the load increases, as this crack width increases, eventually this bond in between the fiber and the paste will break down, and then the fiber will simply be pulled out or simply come out of the paste. That's the most common failure mechanism. It's possible that the fiber itself splits into two, but that's much more difficult to do. What you will also see is then the bonding with the cement is actually a function not just of the material of the fiber as well as the paste, the material properties of the paste. It's also property of the length of the fiber. The longer the fiber, the more length along which the bonding takes place, and therefore the greater force required to break that bonding. And so the two figures I have over here, this is when you have relatively short length, this is when you can have a relatively long length. Both could be the same fiber, they could be the same material, they could be the same cement paste, but the second one, because it's much longer, it will have simply more area or more length of bonding, and because of that, it's going to require greater force or greater stress in order to cause any pull apart or cause breakdown of that bonding. Okay, so there are generally two types of fibers based on length. We saw that there are two types of fibers based on material, that is artificial fibers and natural fibers. Based on length, we have two types of fibers, microfibers and macrofibers. And that's basically based on the length of the fibers. So microfibers have a length of up to 20 millimeters. 20 millimeters, around this much. So microfibers have a length of up to 20 millimeters, and if the length is greater than 20 millimeters, we call them macrofibers. So micro versus macro. The key difference between these two is, as I said in this slide over here, it is the length of the fiber which has a very, very critical role in understanding the behavior of the crack propagation. So if the length of the fiber is very long, it's going to significantly affect how the crack is initiating, how the crack is propagating. If the length of the fiber is short, it will also have an effect, but it will have a different type of effect. We'll see the effect in a second. So that's why we have these two separate classifications, up to 20 mm and greater than 20 mm. Typically, the diameter of a microfiber tends to be around 0.2 to 1 mm, and the diameter of the macrofiber is typically less than 0.1 mm. Now, this is basically, it doesn't have too much of an effect from a pavement design perspective. This is due to manufacturing constraints. So it's easier to manufacture. When you manufacture these fibers, there is certain aspect ratios which are relatively easy to manufacture based on the die. So if you have a relatively short fiber, it can be a thicker fiber. If you have a relatively long fiber, the manufacturing process will require to be relatively thinner. So that's why we have these two fibers. They differ on length because that has the effect on crack propagation. They also differ on diameter, but that's largely because of manufacturing process. The key difference between these two, why we study these two separately, is microfibers, which have a length of less than 20 mm. Microfibers improve the plasticity of the concrete. We'll talk about this in a second. They improve the plasticity of the concrete, whereas macrofibers improve the strength of the concrete. So plasticity versus strength. Let's look at it through this figure over here. So this is a stress strain curve. I'm sure all of you have seen this in the past. This solid black line over here is the behavior of PCC, so plain cement concrete. So obviously, initially, all of you know, up to a certain length, stress is up to a certain region, stress is proportional to strain, and that's what we would call the elastic region. Beyond that, after a certain point, what happens is the stress starts decreasing. That's usually when we assume that we've entered some sort of non-linear regime. Actually, the non-linearity we entered even before that. We do have a small region of plastic strain, but we assume that there's some non-linearity post-peak, that after the peak stress is reached, then we fully enter into a non-linear regime, and the material is actually, in this particular case, the material is softening. That is, as the strain is increasing, the change in the stress is also less. So that means we need to apply less strain in order to generate a certain amount of stress. So this is the general behavior of plain concrete. Now, let's see what happens when we add a microfiber. When we add a microfiber to it, it's what this dotted line is. You'll see that the strength is basically the same. That after the addition of the microfiber, it also reaches a strength at more or less the same strength of as a PCC pavement as a plain pavement. This is why I said over here, microfibers improve the plasticity. So they have no effect on strength really. The strength more or less stays the same. What changes is the post-peak behavior. So PCC, or just plain concrete, is what we sometimes call as a quasi-brittle material. So what that means is that after the peak stress is reached, the strength of the concrete goes down very rapidly, so the stress falls very quickly. The effect of adding microfibers is that post-peak behavior tends to get stretched out much more. This is what we call, what I wrote here, the plasticity. That is, it's after this peak that the macrofibers, the PCC with microfibers or micro FRC, it does not break that easily. And that's because of that bridging effect that we saw, that when we have a microfiber and a crack is starting to form. This peak, by the way, is formed when this crack initiates. So when this crack is starting to propagate, the propagation of the crack becomes arrested by the presence of these fibers. And that's what this peak here basically represents. So the peak stays the same because the crack forms in both cases in the concrete, in the plain cement paste. But because of the arresting of the crack propagation due to the fiber, the post-peak behavior is significantly different when we have micro FRC. It basically stretches out much longer, or to put it in mechanics terms, it becomes a much more plastic material. Now, when we add macrofibers, I wrote from macrofibers improve the strength of the concrete itself. So what I've drawn over here from macrofibers, here the strength itself, the strength being the maximum stress, the strength itself increases. And that's basically because the macrofibers are much longer in length. So because they're much longer, they tend to be more distributed to a much greater extent around the entire concrete, and therefore they can very quickly arrest the development of the crack. And that's why, compared to FRC, macro FRCs tend to increase the strength of the material or strength of the concrete itself. So that's the difference between FRC when we have microfibers versus when we have macrofibers. In one case, micro FRC improves the plasticity of the material. That is, the strength stays the same. It's the post-peak behavior that tends to get elongated. Whereas microfibers, they tend to have a little bit of effect on post-peak, so even the post-peak gets spread out. But what it really does is it improves the strength, so it increases the strength of the concrete. In general, in rigid pavements, we tend to use microfibers. The reason for that is quite simple. It's because it's much easier to mix together. Macrofibers, because they're so long, they have a tendency to get bunched up or balled together, or particularly around coarse aggregates. So it's a little bit difficult to mix macrofibers into concrete to create FRC. There are still ways to do it, but given the vast volumes required for rigid pavements, it's difficult to do for rigid pavements. Whereas microfibers do not have this problem, relatively easy to mix around, you don't need very specialized equipment either, and can be done in large volumes. So mostly in rigid pavements of JPCP applications, we tend to make a lot of use of micro FRC. Okay, so what are the benefits of using FRC? And particularly, I mean micro FRC, even macro to an extent. What are the benefits of using them? So firstly, you should know there's actually a lot of experience of its use, including in India. There are many examples all over the world, including in India, on the use of FRC for rigid pavements. And therefore, the benefits that have been found are as follows. It has been found to have improved resistance to cracking. That I think was already quite clear, as I pointed out previously that when you have this fiber and a crack is trying to propagate, it arrests the propagation of the crack. So there's improved resistance to cracking. That then leads to reduced crack widths, that because of this arresting of the concrete, of the arresting of the crack width can only grow that much, and then beyond that the fiber is preventing the crack width from increasing. Another way to look at it is the fibers tend to hold the crack together more tightly than if they were not there, and so they reduce the crack width. Similarly, they reduce the crack thickness meaning how far the crack has penetrated into the concrete, and they increase the allowable joint spacing. Now, this is an interesting thing. They increase the allowable joint spacing. Remember, if you have longer joint spacing, then effectively you're increasing the stress. If you're increasing the stress, you are going to start having more cracks. But if you can ensure that those cracks are small, that the crack width is small, you might be able to live with having more cracks. In which case, you can effectively increase your joint spacing because the cracks are not that detrimental to functionality as otherwise. So that's why you can increase the allowable joint spacing if you use FRC. By the way, why would it be useful to increase the allowable joint spacing? As I pointed out in a much earlier lecture, the problem with joint spacing is the joints have to be sawed. That is a very labor-intensive process that requires a saw, there's rent, etc., equipment for the saw. So if you have more number of joints, that is, if the joint spacing is relatively small, that tends to increase costs quite a bit. So if you can increase the joint spacing, in other words, decrease the number of joints in a given length of the project, then that makes it a more economical project. So although it is true that addition of these fibers obviously is going to cost money, so there's a slight economic cost to this, but the economic cost can more than be made up by the fact that you could increase the joint spacing as well as these other benefits which you get relative to performance. Okay. So there are many specifications for FRC. FRC, by the way, is not something which is specifically used only in JPCP or in pavement engineering. FRC you will find, well, first of all, you'll also find it in asphalt or in flexible pavements, but FRC is actually something that has very wide applications in structural engineering. So if you ever want to understand how to develop a mixed design with FRC or how to characterize FRC, we can actually look at the structural engineering codes all over the world to see how they do it. So here are certain codes which you will find if you just open up Google or open up a search engine and try to look for standard codes for FRC, you will find a number of them. So one of them is the British Concrete Society's TR34, so that's technical reference number 34. ACI, the American Concrete Institute, has their specification number 360, which is for FRC. IRC SP 46, which I've already talked about, special publication 46 in India, which is for FRC. And then perhaps the most important one, the one which we will talk about in more detail today and the one which is used quite widely, is actually ASTM C1609. This is a very important one because the guidance from C1609, and I'm just going to call it 1609 for short, the guidance from ASTM C1609 is actually what is used in IRC SP 46. So we will then see how that works. Okay, so let's go into 1609. Again, I mean, when I say 1609, I mean ASTM C1609, the latest revision of it. I'm just in short calling it 1609. So 1609 is for FRC with microfibers, that is those which cause improved plasticity. These are what are used commonly in rigid pavements. You could also use macrofibers. Nothing to stop you from using macrofibers in rigid pavements, but what I said a few minutes ago, it tends to have certain practical limitations, particularly relevant to mixing. So more traditionally, we use micro FRC for rigid pavements. So 1609 is actually for rigid pavements with micro FRC. And again, what happens when you add micro FRC, when you add microfibers to concrete is you get this long tail, you get this plastic behavior. So it's the improved plasticity, and the purpose of this code ASTM C1609 is to actually characterize this improved plastic behavior. Okay, so let's talk about how that, and this characterization of improved behavior actually happens by looking at the flexural strength of the material. So we are all familiar with the conventional meaning of flexural strength, that is the nominal strength at maximum load under, let me just add this, under flexure. So I'm sure all of you have seen this test. So basically we have a it's not simply supported, it's simply supported beam with an overhang, and then we apply a load. Either we apply a single load or we might apply two loads distributed. So that tells us whether we have a 3-point test or a 4-point test. And what we do is for plain concrete, we apply this load and we keep measuring the stress versus the strain until we reach a maximum, that is until a crack just begins to form. Once the crack forms, whatever that maximum load was, let's say that was P, the nominal strength at that maximum load under this flexural loading is what we call the conventional flexural strength. The key aspect to understand that, and that by the way is also what I showed over here, this dark black line for PCC, that's basically, that could come out of a flexural strength test. The key to understand over here is, in this characterization, in this way of analyzing or characterizing the flexural strength of concrete, we are only accounting for the formation of the crack. In other words, what is the maximum load. We are not taking into account what is happening after the maximum load. And in other words, we are not taking any consideration of post-peak behavior. And the reason for that is, for conventional concrete or plain concrete, post-peak behavior, there's not much in terms of post-peak behavior. You have a rapid disintegration of the material or rapid propagation of the crack. So there's not too much really to look at that after that. But when we add FRC with microfibers, we actually improve the plasticity. That is, this post-peak behavior is no longer just a rapid decline in the strength, but we actually get a fairly gradual decline in strength. That is, the post-peak behavior tends to be spread out much more. So the philosophy of ASTM C1609 is, in addition to characterizing the strengths of the concrete in terms of the formation of the crack, or what is called crack initiation. Instead of limiting the strength definition to just crack initiation, some amount of consideration is also provided for plastic behavior post the maximum load. That is, we have to somehow take this post-peak behavior also into account while characterizing strength. And 1609 then tells us how to do that. All right, so let's look at an example, and this I've taken directly from ASTM 1609. Here we basically have a load versus deflection curve. You could say this is also a stress versus strain curve, but this is a sort of more granular data. This is load versus deflection. So what we see here is, initially, when we apply a deflection and we look at how much load is required to apply that deflection, we have a more or less linear behavior. This is identical for PCC as well as for micro FRC. And the strength, the maximum load then reaches some value, which we can call PP or Pmax or P1, whatever. This then gives us the flexural strength of the plain concrete. This is what we call the peak load. This is the flexural strength of the plain concrete. Sometimes it can also be called the first peak load. But now what happens is, again, we are interested in the post-peak behavior. So in the post-peak behavior, we then look at the behavior after the peak, and this is what it might look like. This is a schematic example that you have a gradual and relatively long decline in the load as you keep applying a particular amount of displacement. Now, what the code actually tells us is to look at you look at the load at two particular values of displacement. By the way, one thing I forgot to define over here is the span. So I can define this capital L as the span of the beam. The span is the distance. Again, it's not a simply supported beam. It's a simply supported beam with some overhang. So the span is actually the distance between the supports of the beam. So what we have here, so that's called the span length. There are two particular deflections, L over 600 and L over 150. We look, in this graph, we actually look at L over 600 and L over 50. And we find what is the corresponding load at those deflections. Now, L over 600 and L over 50 are actually much higher than what you can call the first deflection or the peak deflection. So the deflection of just the plain concrete is not that much. The deflection of L over 600 and L over 150, as you can imagine, typically in this code, this L value is 450 mm typically. So you can calculate L over 600 and L over 150, you see it's maybe 3 mm or 1 mm or something of that sort. It's much, much more than what you would get for this peak load. So we look at L over 100 and L over 160, we draw these two vertical lines, intersect the curve, and then we see what is the corresponding loads. Those corresponding loads we define with the symbol P150 and P600, where P150 corresponds to the load at a deflection of L over 150 and P600 corresponds to the load at a deflection of L over 600. So we first experimentally derive this curve, we conduct the experiment, we get this curve, and then we using this at L over 600, L over 150, we find P600 and P150 respectively. So the principle, this load as we call it, this is what we call the residual load. The principle of ASTM C1609 is as follows. The FRC specimen can sustain higher loads than just the peak. That is, failure of the material doesn't happen just very soon after the peak. It's gradual after the peak, and therefore loads can be sustained even beyond the peak loads. So we consider the load at L over 600 and L over 150, which we call the residual load values. So these two values which I have shown previously, P600, which corresponds to L over 600, and then P150, which corresponds to L over 150. These are two values which we call residual loads. The residual load, then, if we take the residual load and we get the nominal strength out of it, that's how you also calculate the flexural strength. If we calculate the nominal strength at the residual loads, then they become what we call the residual strengths. That is basically, you take this load, and again, this is not a structural engineering class, but basically what happens is, at those corresponding loads, you can draw the bending moment diagram. The bending moment diagram will look like this. If you have a 4-point test, it will look like this. If you have a 3-point test, from the bending moment diagram, you can then calculate what is the moment. From the moment, you can calculate the stress, and that's the nominal strength. So we can take this P over 600, and then we can calculate the residual strength for using that. That's the nominal strength. So that gives us the residual strength. The assumption made in 1609 is this residual strength can simply be added to the flexural strength to get a so-called effective strength. That is, based on this peak load over here, I can calculate a flexural strength. That is what I've been calling FR so far. Idea is, to FR, I can then add an F150. That is, from this P150, I can calculate F150, which is the strength. So P is the load at L over 150. F150 is the residual strength or the nominal strength at P150. So I can calculate this, and I simply add these two up. And this gives me something which might be called an effective flexural strength of the material. I put a question mark over here. The reason I put a question mark to this approach of simply adding it is that this is actually not consistent with nonlinear mechanics. In nonlinear mechanics, you cannot simply, well, the reason being, this strength is being calculated, this F150 strength is being calculated based on linear mechanics. You cannot do that, because once you have post-peak behavior, you've actually gone into nonlinear mechanics. So this approach of simply adding these two strengths, adding the flexural strength and adding the residual strength, that's actually something that does not agree with, that's not technically correct mathematically. It does not fully agree with what you should be doing with nonlinear mechanics. Nonetheless, as I've pointed out in earlier lectures, nonlinear mechanics is hard. So at least this is a relatively easy way to approach this problem, and that's why 1609 recommends this. By the way, there are two values which I just put over here. You can do the effective strength is FR plus F150, or you can do FR plus F600. Which one should you use? Well, that depends. Your choice of which one to use depends basically on how conservative you want to be. F150 is lower than F600. So if you use F600, which corresponds to P600, you're going to be increasing the flexural strength by more than if you use F150. And it can actually be a fairly large difference, and not very small differences either. So whether to use F150 or to use F600 to characterize FRC, that's a question of how conservative do you want to be in your design. There is no explicit guidance as such on what to use. You use either depending on how conservative your design is. So for example, if you're doing this for an expressway, you might use F150. If instead you're doing it, let's say for a local road, you might just use F600. Okay. This F160, F600 is actually what we call, it can also be defined separately. We can then divide it by FC. So if we had F150, we can divide it by FR, and that we call R150, which is called the residual strength ratio. By the way, one piece of notation, I've been writing F150, and similarly we can have R600, which is F600 divided by FR. Sometimes in this case, you also see a little bit of a superscript placed over here, 150, 150 over here. This superscript which I'm writing over here, this represents the span of the beam, L. So it's just saying what is the span of the beam. Sometimes you see it used, sometimes you won't see it used. It's just an additional notation over there. Okay, so what we get is then, to summarize what we find from 1609, we experimentally derive this graph. From this graph, at L over 600 and L over 150, we can calculate P150 and P600. These are called the residual loads. The residual loads can then be converted to an equivalent strength, that's a nominal strength, and that gives us the residual strength. To the residual strength, we can add the flexural strength, which we get at the first peak load, and that gives us the effective strength. Or another approach is we can then we can take the residual strength, we divide it by the flexural strength, and then we get the residual strength ratio. This residual strength ratio is particularly important because it gives us guidance in IRC SP 46 on how to further take into account the behavior under cyclical loading. So we'll see that in a second. Okay. Again, the choice of which load, whether it's F150 or F600, it depends on the designer. One of them is more conservative, one of them is less conservative. We already talked about that. There is a second method to calculate residual strength. The first method to calculate residual strength, as I told you, is just get whatever this peak load is, and then for that peak load, you calculate the nominal strength. That's one way to do it. There is a second method which is actually based on toughness. Toughness is the area of the load deflection graph. So if, for example, I take deflection at L over 50, previously I was saying, okay, just use this value of P and call it P150. That's one approach. Another approach is to actually take the area of the graph up to a deflection of L over 150. And then you can use these two formulas over here. It could be L over 600 or L over 150. You get that, we call that T150 or T600, depending on where it's being done. And then you can use these two formulas to calculate F150 or F600. So this method 2 is actually based on area or toughness, whereas method 1 is based on a point value. Method 2 tends to give you a little more stable value for across different materials. So your variance between different materials is a little lower if you use method 2 than if you use method 1, but it's really a choice of the designer as to which method they want to use. So here is some data. Again, I got this from some previous slides from when I was a student. So here is some data on what these curves look like. So what we have in blue over here, down here, this is plain concrete. So as you can imagine, it rises to some peak strength and then very, very quickly deteriorates and the material breaks down very, very quickly over a very, very short length. But once you start adding more fibers, so here is different percentage of fibers as well as different types of fibers. So you can have some synthetic fibers, you can have some crimpled fibers, hooked fibers, different geometries of fibers. You clearly see this very large post-peak behavior which forms. And indeed, it seems, at least for this synthetic fiber, it's persistent, that basically the fiber is just not breaking and you are basically having a very large beam deflection for almost a constant stress, that you've essentially created a completely plastic material. This might be a particularly idealized case, but there are other cases also where the deterioration in the FRC is very, very slow. So this is one example of what a residual curve, stress curve could look like in practice. So what I have shown you here, this was sort of from 1609, this was kind of a schematic, but here is some real experimental data and you see the schematic is pretty spot on with this sort of data. Okay, and then for each of these which I have shown, so for these 5 different materials, what they went ahead and calculated here is R150, which is the residual strength ratio. And what we see is, of course, for plain concrete, the residual strength ratio is 0. We don't have a residual strength if you don't have fibers. But for the others, you'll see the residual strength can be 18%, 24, 34, 32. So it's generally in that range. Let's say, just for the sake of assumptions, it can be 15 to 40% residual strength, which you'll agree with me is not a small number. If we are remember, the purpose of calculating residual strength is then we are taking the effective strength is equal to FR plus this residual strength. And this effective strength is used to calculate our stress ratio. So if we are increasing the stress ratio by, let's say, 15 to 40%, if we are increasing the strength by 15 to 40%, we are decreasing the stress ratio by that much. And when you do that, you have significant changes in the fatigue damage because those SN curves are very, very sensitive to the stress ratio. They are logarithmic after all in N. And so it's very important to take this behavior into account. We could still use FRC and assume that this doesn't exist and do FRC design exactly as PCC design. That would be excessively conservative. You are really underestimating the strength of the material by something around 15 to 40%. So IRC SP 46, which I had previously talked about, these are guidelines for design and construction of fiber reinforced concrete pavements. These are guidelines. It's not fully a legally reinforceable code, but in the near future, it might become one. Okay, so what are some guidelines which are used? So what I gave you in 1609 was the scientific analysis of FRC. But if we had to look at how you do it in practice for design purposes, where you may not have the luxury to do all the testing, then this is what is recommended in this particular special publication. Now, one little piece of notation, the notation I showed you previously, which was this F150, R150, etc., that is the notation from ASTM C1609. IRC SP46 makes a slight deviation from the notation, but it's not too serious, but I just want to point out the difference. It defines something called an FCTK, which is that flexural strength. K here represents characteristics, so it's the 95th percentile flexural strength after the first week. And then FE150K is the 95th percentile to use as the design value. This is the same as F150 over 150. And so this value, so FE150K divided by FCTK is what we were previously calling this R150, the residual strength ratio. And the recommendations is that the residual strength ratio is a function of the thickness of the FRC layer itself. This, I'm not quite sure this is scientifically correct, but it's just an observation which is being used for the sake of design. It's an empirical observation. I'm not sure it stands up to mechanics. But anyway, it says that if you have a 50 mm thick FRC, you can assume a residual strength of around 40%. If it's 100 mm, then you assume a residual strength of 30%. Of course, if you should be conducting the actual test, in the absence of that, these are the first set of guidelines which are used in the special publications. The residual strength is recommended is calculated using the toughness method. So that area under the curve method I talked about, method 2, it's calculated using that method. And when you're pouring it for conducting the test, it is recommended to pour as follows: pour in the middle and then pour on the sides. This is to make sure that you have a uniform distribution of the fibers. And the most important thing which I wanted to get to here, for design purposes, so what you do is you test the material, you calculate F150, you calculate R150. Of course, you do it for 95th percentile, hence it has to be the characteristic value. The most important recommendation which IRC SP46 makes is as follows: if the residual strength ratio is 0.3, that is, if it's low dosage or less effective fibers, then the endurance limit can be increased from 0.45 to 0.5. This is why I had taken some time in the beginning of today's lecture to remind you what is that endurance limit. On the SN curve, it is that value of S below which the number of allowable repetitions goes to infinity. This is the endurance limit. So what it says is that if you have fiber reinforced concrete and the residual strength ratio is less than 0.3, then the endurance limit can be increased from 0.45 to 0.5. You can have a small increase in the endurance limit. Whereas if you have R150 or the residual strength ratio greater than 0.3, that is, you have substantial amount of toughness added by the material, then the endurance limit can be increased from 0.45 all the way to 0.6. That's a 30% increase. That's quite a lot. So, and if you recall the calculations we did in the previous lecture for JPCP design, when you increase the endurance limit like this, you are basically putting what increasing the endurance limit means that for larger and larger axle load parts of the axle load spectra, you are allowing an infinite number of repetitions. You are significantly going to decrease the fatigue damage and hence the cumulative fatigue damage. So just increasing from 0.45 to 0.5, it might seem like a small thing. It's actually a very big thing. It's particularly from 0.45 to 0.6 has a significant effect on fatigue damage. But how much effect? That I will leave for you to do the calculations yourself. Okay, some final thoughts on FRC. So FRC generally requires higher slump. That is, when you're mixing a fiber reinforced concrete, you don't do the mix design identical to conventional concrete. Generally, you do require some amount of higher slump. You don't add water to that because you're going to decrease strength. So it does involve adding some superplasticizer. The mix design, therefore, has to be adjusted accordingly. It is very important in mixing fibers in FRC that the fibers be dispersed uniformly. You cannot have clumping. The problem with macrofibers is they tend to have a lot of clumping. So that's basically one reason to avoid that. We use microfibers, but even they can have clumping. So it is important to ensure that no clumps are formed. You can either add it with the coarse aggregate or there is a separate process. That is, you can put the coarse aggregates into the mixture. Then you add the fibers, you mix them around, and then you can start pouring the water and the cement, etc. Or you can completely do the mix of the cement and the concrete itself and then add the fibers during that process. Both are fine, but the key is fibers should never be added first. Never first put fibers and then put coarse aggregate and then put cement. You are asking for clumping to happen. So it's very important that fibers either they're added after the coarse aggregate or they're added after the cement and water have been mixed. They should not be added to the beginning of the process. And finally, homogeneity should be checked. So what is recommended is that by this SP46 is that the material should be sampled. Every time you mix some FRC, sample a little bit of it, take it through a 5 mm sieve, mix it around, pour water around it, remove the cement, and then see whether you have any clumps of fibers forming. The average weight of fibers obtained is determined from nominal fiber dose. It should not be less than 90% of the specified fiber dose. So in other words, you should not have a large amount of clumping which is happening. You should have a uniform, homogeneous distribution of the fibers. And this particular guideline tells you how to achieve exactly that. Okay, so that completes our lecture on fiber reinforced concrete for JPCP. Our last lecture, which will be in the lecture number 40, we will actually talk about design of CRCP. So I had promised you that JPCP and CRCP follow very closely to each other. We had one exclusive lecture on CRCP in our discussion for ASH to MEPDG, and therefore our last lecture is going to be a discussion of CRCP for the Indian context, and that's going to be based on IRC 118. So I will see you in that lecture.